Space, Time, and the Eye of the Beholder. In June 1905, 26-year-old Albert Einstein submitted a technical article to the Annals of Physics in which he came to grips with a paradox about light that had first troubled him as a teenager, some 10 years earlier. Upon turning the final page of Einstein's manuscript, the editor of the journal, Max Planck, realized that the accepted scientific order had been overthrown. Without hoopla or fanfare, a patent clerk from Bern, Switzerland, had completely overturned the traditional notions of space and time, and replaced them with a new conception whose properties fly in the face of everything we are familiar with from common experience. The paradox that had troubled Einstein for a decade was this. In the mid-1800s, after a close study of the experimental work of the English physicist Michael Faraday, the Scottish physicist James Clerk Maxwell succeeded in uniting electricity and magnetism in the framework of the electromagnetic field. If you've ever been on a mountaintop just before a severe thunderstorm or stood close to a Van de Graaff generator, you have a visceral sense of what an electromagnetic field is, because you've felt it. In case you haven't, it is somewhat like a tide of electric and magnetic lines of force that permeate a region of space through which they pass. When you sprinkle iron filings near a magnet, for example, the orderly pattern they form traces out some of the invisible lines of magnetic force. When you take off a wool sweater on an especially dry day and hear a crackling sound and perhaps feel a momentary shock or two, you are witnessing evidence of electric lines of force generated by electric charges swept up by the fibers in your sweater. Beyond uniting these and all other electric and magnetic phenomena in one mathematical framework, Maxwell's theory showed, quite unexpectedly, that electromagnetic disturbances travel at a fixed and never-changing speed, a speed that turns out to equal that of light. From this, Maxwell realized that visible light itself is nothing but a particular kind of electromagnetic wave, one that is now understood to interact with chemicals in the retina, giving rise to the sensation of sight. Moreover, and this is crucial, Maxwell's theory also showed that all electromagnetic waves, visible light among them, are the epitome of the peripatetic traveler. They never stop. They never slow down. Light always travels at light speed. All is well and good until we ask, as the 16-year-old Einstein did, what happens if we chase after a beam of light at light speed? Intuitive reasoning, rooted in Newton's laws of motion, tells us that we will catch up with the light waves, and so they will appear stationary, light will stand still. But according to Maxwell's theory, and all reliable observations, there is simply no such thing as stationary light. No one has ever held a stationary clump of light in the palm of his or her hand. Hence the problem. Luckily, Einstein was unaware that many of the world's leading physicists were struggling with this question, and were heading down many a spurious path, and pondered the paradox of Maxwell and Newton largely in the pristine privacy of his own thoughts. In this chapter, we discuss how Einstein resolved the conflict through his special theory of relativity, and in so doing forever changed our conceptions of space and time. It is perhaps surprising that the essential concern of special relativity is to understand precisely how the world appears to individuals, often called observers, who are moving relative to one another. At first, this might seem to be an intellectual exercise of minimal importance. Quite the contrary, in the hands of Einstein, with his imaginings of observers chasing after light beams, there are profound implications to grasping fully how even the most mundane situations appear to individuals in relative motion. Intuition and its flaws. Common experience highlights certain ways in which observations by such individuals differ. Trees alongside a highway, for example, appear to be moving from the viewpoint of a driver but appear stationary to a hitchhiker sitting on a guardrail. Similarly, the dashboard of the automobile does not appear to be moving from the viewpoint of the driver, one hopes. But like the rest of the car, it does appear to be moving from the viewpoint of the hitchhiker. These are such basic and intuitive properties of how the world works that we hardly take note of them. Special relativity, however, proclaims that the differences in observations between two such individuals are more subtle and profound. It makes the strange claim that observers in relative motion will have different perceptions of distance and of time. This means, as we shall see, that identical wristwatches worn by two individuals in relative motion will tick at different rates, and hence will not agree on the amount of time that elapses between chosen events. Special relativity demonstrates that this statement does not slander the accuracy of the wristwatches involved, rather, It is a true statement about time itself. Similarly, observers in relative motion carrying identical tape measures will not agree on the lengths of distances measured. Again, this is not due to inaccuracies in the measuring devices or to errors in how they are used. The most accurate measuring devices in the world confirm that space and time, as measured by distances and durations, are not experienced identically by everyone. In the precise way delineated by Einstein, special relativity resolves the conflict between our intuition about motion and the properties of light, but there is a price. Individuals who are moving with respect to each other will not agree on their observations of either space or time. It has been almost a century since Einstein informed the world of his dramatic discovery, yet most of us still see space and time in absolute terms. Special relativity is not in our bones, we do not feel it. Its implications are not a central part of our intuition. The reason for this is quite simple: the effects of special relativity depend upon how fast one moves, and at the speeds of cars, planes, or even space shuttles, these effects are minuscule. Differences in perceptions of space and of time between individuals planted on the Earth and those traveling in cars or planes do occur, but they are so small that they go unnoticed. However, were one to take a trip in a futuristic space vehicle traveling at a substantial fraction of light speed, the effects of relativity would become plainly obvious. This, of course, is still in the realm of science fiction. Nevertheless, as we shall discuss in later sections, clever experiments allow clear and precise observation of the relative properties of space and time predicted by Einstein's theory. To get a sense of the scales involved, imagine that the year is 1970 and big, fast cars are in. Slim, having just spent all his savings on a new Trans Am, goes with his brother Jim to the local drag strip to give the car the kind of test drive forbidden by the dealer. After revving up the car, Slim streaks down the mile-long strip at 120 miles per hour while Jim stands on the sideline and times him. Wanting an independent confirmation, Slim also uses a stopwatch to determine how long it takes his new car to traverse the track. Prior to Einstein's work, no one would have questioned that if both Slim and Jim have properly functioning stopwatches, each will measure the identical elapsed time. But according to special relativity, while Jim will measure an elapsed time of 30 seconds, Slim's stopwatch will record an elapsed time of 29.999999999999952 seconds, a tiny bit less. Of course, this difference is so small that it could be detected only through a measurement whose accuracy is well beyond the capacity of handheld stopwatches run by the press of a finger, Olympic quality timing systems, or even the most precisely engineered atomic clocks. It is no wonder that our everyday experiences do not reveal the fact that the passage of time depends upon our state of motion. There will be a similar disagreement on measurements of length. For example, on another test run, Jim uses a clever trick to measure the length of Slim's new car. He starts his stopwatch just as the front of the car reaches him and he stops it just as the back of the car passes. Since Jim knows that Slim is speeding along at 120 miles per hour, he is able to figure out the length of the car by multiplying this speed by the elapsed time on his stopwatch. Again, prior to Einstein, no one would have questioned that the length Jim measures in this indirect way would agree exactly with the length Slim carefully measured when the car sat motionless on the showroom floor. Special relativity proclaims, on the contrary, that if Slim and Jim carry out precise measurements in this manner and Slim finds the car to be, say, exactly 16 feet long, then Jim's measurement will find the car to be 15.9999999999997 feet long, a tiny bit less. As with the measurement of time, this is such a minuscule difference that ordinary instruments are just not accurate enough to detect it. Although the differences are extremely small, they show a fatal flaw in the commonly held conception of universal and immutable space and time. As the relative velocity of individuals such as Slim and Jim gets larger, this flaw becomes increasingly apparent. To achieve noticeable differences, the speeds involved must be a sizable fraction of the maximum possible speed, that of light, which Maxwell's theory and experimental measurements show to be about 186,000 miles per second, or about 670 million miles per hour. This is fast enough to circle the Earth more than 7 times in a second. If Slim, for example, were to travel not at 120 miles per hour but at 580 million miles per hour, about 87% of light speed, The mathematics of special relativity predicts that Jim would measure the length of the car to be about 8 feet, which is substantially different from Slim's measurement, as well as the specifications in the owner's manual. Similarly, the time to traverse the drag strip according to Jim will be about twice as long as the time measured by Slim. Since such enormous speeds are far beyond anything currently attainable, the effects of time dilation and Lorentz contraction, as these phenomena are technically called, are extremely small in day-to-day life. If we happen to live in a world in which things typically traveled at speeds close to that of light, these properties of space and time would be so completely intuitive, since we would experience them constantly, that they would deserve no more discussion than the apparent motion of trees on the side of the road mentioned at the outset of this chapter. But since we don't live in such a world, these features are unfamiliar. As we shall see, understanding and accepting them requires that we subject our worldview to a thorough makeover.